Okay, we have something a little different here today. We want to find all primitive roots mod 23. Now, I think a lot of this stuff I haven't went over before, so I probably haven't properly set this up, but we'll try to explain some of it. So to start with, I think I should discuss what is a primitive root. Well, let's create something. I'll call this A, and what we'll want is we'll set A as an integer between 0 and 23. The reason for that is mod 23, any other values outside of this A, there's gonna be a congruent A to it. Like if we just said something, if we had 27, that's gonna be congruent to 4 mod 23, and so we have an A value 4. And then for A to be a primitive root, what we're gonna want is we're gonna say we want the order of A, mod 23, to be equal to Euler's totient of 23. We can call this thing P just for notation. And I won't really go over how the totient is calculated, but for a prime, it's just going to be the prime minus 1. So we could have this formula. Euler's totient for a prime number P is just going to be equal to P minus 1. And then you might wonder, what is the order? To find the order, we could look at A to the K, where this is going to be congruent to 1 mod 23. And so the order on this is going to be the least K value that gives us 1. So for this to work, so for A to be a primitive root, we would have K equal to 22, just because using this, Euler's totient of 23 is going to be 22. So we need these things to match for it to be a primitive root. Now, one other thing I want to go over before we start checking roots, because we're basically going to want to check all these. I wanted kind of a large number to show how tedious it can be, but not that large of a number. So that's why I went with 23 on this. You could go, I guess it would be impractical for a really big number, but we're going to be checking all of them. And one thing I want to mention about 23 wasn't an accident. 23 is actually a safe prime. So how it works, we have the Sophie Germain primes. So for a Sophie Germain prime, we'll call this thing K. And for this prime K to be a Sophie Germain prime, if we just take 2K plus 1, this thing is also going to produce a prime. In our case, this 23 value. So for this to work, you'll notice the K value needs to be 11. So we have the case where the Sophie Germain prime is actually the 11. The 23, we call this a safe prime, the output of it when we do 2K plus 1 on it. And so my motivation for the video is to show how this is going to simplify our search for primitive roots. Because otherwise you could do it, I mean, there's different ways. You have to go through checking all the exponents. It's a longer process and it becomes really tedious, but this is going to definitely save some of the work. So let me get rid of all this and we'll take a look at all the values we need to check. Okay, now we have here all the values I want to check. You will notice there's a few values missing. I said A, like these are all our A values, and I said they're coming between 0 and 23. So we're missing 1, 4, 9, 16, 22. Although 22, that was a mistake. I actually want 22. But the other ones I want to leave off because those are perfect squares. I leave those off because the perfect squares can never be primitive roots. I don't know if there's an exception, possibly 1 mod 2. I'm not really sure on that one, but I'm just concerned with odd primes for this P value. So otherwise, generally, you're never going to have the perfect square. So we're just leaving those off. Those are not going to be primitive roots. The reason for that, let me give you the check that we have for primitive roots. So if we take phi of our P number 23, we get 22. And then we can factor this into its prime factors. Again, because of the setup where I have it as a safe prime, it's real nice because we already know the totient always gives an even number for an odd prime. So we're always going to have a 2. And then it's set up where it's just going to be one other prime, right? This factorization can be much more complicated. But here, with the way we have it set up with the safe prime, we know it's going to have this very simple setup. And then our check to see if it's a primitive root, it's just going to be A raised to this value. We'll write it like this. We'll keep it general. So it's going to be A raised to the totient over a prime factor. So we have to go through all the prime factors. In this case, it's just this 2. So we could like label this like P1, P2. And for it to be a primitive root, we need this to be not congruent to 1 mod P for all of these P's. And so the reason I eliminated all the perfect squares is for any of them, we could write it like some value squared. I'll just do like an example, like for 9, I can write 9 as 3 squared. And then with our phi of p, this is going to be 22. You plug in 11, one of these, this thing here is going to be 2. And the way we have this set up, we're always going to get a 2 as an exponent, because just as the way we have it with a safe prime, it's always going to factor as 2 times some prime. And so for an example, we'll just take the 9 that I left out right here. I can write it as 3 squared. Using this, we can take our totient of p, which is 22, and then we know that we're always going to have an even number, so we're always going to have a factor of 2. So we have this 2 here, and we look at this mod p. But then with exponent properties, we can just cancel the 2's, and this is congruent to 3 to the 22 mod p. But this always has to be congruent to 1. That's Fermat's little theorem. So that's actually like the maximum the order can be is going to be 22. So we know that this is going to be a primitive root because Fermat's little theorem tells us this always needs to be 1. So because this fails, we know it's not a primitive root. So now for the shortcut on this, let's look at 2. And what I'm going to do is I'm going to use some notation. I want to look at the Legendre symbol of 2 mod 23. We want to say, for this notation, what this means is it's saying, is 2 a quadratic residue mod 23? Well, it's not obvious at first because 2, we don't think of it like a perfect square. But there is kind of an intuitive way that you might see. Think about if we have 25 mod 23. 25 is obviously a perfect square. But if we reduce it mod 23, we get 2 mod 23. So on this, yes, this is going to be a quadratic residue. What we use is 1 to say it's a quadratic residue, minus 1 to be a non-residue. So we can just fill in our table with a 1 right there. Next, we'll go to 3, doing the same kind of thing. Now, the thing about this, these can be kind of tedious to calculate unless you kind of know some of the tricks and rules on it. For 3, we have a rule that says if our mod is going to be plus or minus 1 mod 12, then this is going to be 1. Well, 23 is 1 less than 24, which is a multiple of 12. So we can say this is going to be 1. This is also going to be a quadratic residue. We skip 4, of course, as we said that's going to be not a primitive root. So actually, all I'm doing right now is figuring out if they're quadratic residues. I'm not even dealing with primitive roots yet. So then for 5, we do this one. Is this one a quadratic residue? Again, we have a rule for 5. It says, if we have something 5 over p, we want to check if the p is 1 or minus 1 mod 5. And 23 is not, that's 3 mod 5. So this is not going to be a quadratic residue. So you might be wondering, why am I just checking quadratic residues and I'm not checking for primitive roots? Well, that goes back to a couple of things. It's the fact that we said this was a safe prime, and that's going to give us a shortcut. It also goes to Euler's criterion, where we're checking all these a values again. What our Euler's criterion is going to tell us is when we have p is going to be a prime, we can check, this is the same thing as checking the totient, right? This p minus 1 we said is the totient, like we did right there. We want to check this right here, and we want to just check this value, mod 23, and if this is congruent to 1, then we say it's a quadratic residue, and if it's congruent to minus 1, we say it's a non-residue. The reason why it's so helpful here is you'll notice this is basically the same check we did before when we checked these 2 roots. If we go back to that, it was a to the p minus 1. I think we wrote it in terms of the totient, and then we were checking both these. But notice this is exact. 2 is actually this p1 right here. I should say this was like pk, but this actually is one of our cases. So there's an overlap there. Our check for the quadratic residues, if we did it out with Euler's criterion, we'd actually be already checking one of our roots. So with this check here, we're pretty much doing a lot of the work, because we said this needs to not equal 1. So if we get this 1 value, right away we know these can't be primitive roots because we already did one of our checks just by checking the Legendre symbol in the quadratic residue. So we can already cross off 2 and 3. So then we'll keep going, checking more of these values, but they go pretty fast this way now. Like one other thing we can use for 6, notice 6 is 2 times 3. So if we're checking is 6 a quadratic residue mod 23, well, we have a property of the Legendre symbol that allows us to break this up. When this number is not prime, we can take it and write it like this, just splitting it up because 2 times 3 is 6. But we already found both these values. This is what we just did. We found this value to be 1, this value to be 1. We multiply them, we just get 1. So we can say 6 is a quadratic residue. We can fill that in, but that also allows us to fill in a bunch of other values, because using the same logic, like 8 is going to be 2 times 2 times 2, 1 times 1 times 1, this value needs to be 1. For 10, doing the same kind of thing, 2 times 5, 1 times minus 1, minus 1. 12, that's made up 2 squared times 3, 1 squared times 1, that one's going to be a 1. This one I don't know yet because I don't get 7 yet. This one is just like 12, it's all made up of 2's and 3's, so this is going to be a 1. And I think that's all we can do. Oh no, actually we can do this, because this is going to be 20 is 4 times 5, 1 squared times minus 1, minus 1. Let's keep going and get our 7 value. So for 7 over 23, this one's a little more tricky. What we need here is the law of quadratic reciprocity, which is going to allow me to flip this thing. So the way this works, we can actually flip the Legendre symbol. There's one check though. We want to check what, these are both going to be odd primes, but is it going to be 1 mod 4 or is it going to be 3 mod 4? There's only 2 possibilities for an odd number. Well, these are both 3 mod 4, and what that tells us is we need to bring a minus sign out front. Any other case, if we've got any 1 mod 4s, then it's going to be positive, but we have to bring a minus sign for this case here. Then here's where we can actually reduce this as if it was a fraction, even though it's not. So when you do that, if you reduce this as a fraction, it's going to be minus 2 over 7. But this is the principle we saw before when I said if you square 3, 9 mod 7 is 2. So this is a perfect square. This value is 1. Another way you can look at it is when the a value is 2, the rule is you check if it's mod 8 plus or minus 1 mod 8, and 7 is minus 1 mod 8. So this has to be 1 times a minus sign. This is going to be minus 1. But then we can get a few more values, like 2 times 7 is 14. 1 times minus 1, minus 1. Same thing with 3. 3 times 7, 1 minus 1, minus 1 here. I think I missed 15. 3 times 5, 1 times minus 1, just doing that split thing we did before. This is going to be minus 1. Again, we can eliminate all the quadratic residues because they can't be primitive roots. Eliminate that one. Next, check 11. Do the same kind of thing. Quadratic reciprocity. Again, both these are 3 mod 4, so when we do the flip, what's going to happen is now we still need the minus sign out front. Reduce it, we end up with, this becomes just 1. Reducing it mod 11 becomes 1 over 11, but 1's a perfect square, so this always has to be 1, minus times 1, minus 1. So we can do that one, and then we can also do 22, it's a multiple of 11, so 2 times 11, 1 times minus 1, this is minus 1. Okay, we just have a few more primes, 13, 17, and 19, so we'll do these kind of quick. Okay, so now we're really close. We have eliminated a whole bunch of values. We have all these minus 1 values as candidates. It's tempting to think and just jump to say these are all primitive roots. It's not quite true. It's close to true in this case where we've chosen a safe prime. It's not even, you wouldn't even really want to guess that normally, but because we have a safe prime, it's almost kind of true. And then what we want to do is, see, one thing we can do, we have this formula for the number of primitive roots where we just take our p and we plug it into this. We want the totient of the totient. We already determined this value here is 22. So we take that and we just now want to calculate phi of 22. Well, the totient is multiplicative when the GCD is 1. We've split this up into its prime factorization. So in this case, we can say this is going to be equal to totient of 2 times totient of 11, the factoring we just found there. But now we have primes, and we can use this p minus 1 thing that we used here. So 2 minus 1 gives 1, 11 minus 1 gives 10, and so our value here for the totient of the totient is just going to be 10. So what we should have up here is 10 primitive roots. If we count all of our non-residues, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One of these is not a primitive root because we want 10. One thing we can do is go back to our check for primitive roots. If this wasn't a safe prime, I would say we would really need to go and check everything. Like that would be the way, and that's why it's tedious, because we have to go through and do, and also it would probably be more primes, right? So if we had to do all that out, that would be pretty slow. Here we don't have to do it, I'm just doing it to show how this works. So what we're saying is our check for primitive roots, it's gonna be this thing where it's the totient over all these primes. And we want this to be not congruent to 1 in order for these to be primitive roots. So we could check, as A, we check every single one of these, right? We plug all these in and check the value. But like I mentioned before, we really already checked this 2 value with Euler's criterion, because that's what Euler's criterion says. It says we plug in 2 here all the time. So that check was already done. We don't have to worry about checking this. And then, so now we know what's left, and we know what in this case, this is the general formula that we want to check, but we know the specifics because we know our totient is 22, and the prime that we haven't checked yet is 11. But then 22 over 11, this is just a squared. But this right here is going to be pretty easy to deal with. Like we would just be checking, like, is 5 squared going to be congruent to 1 mod 23? I mean, you could run through it that way and just square each of these, but that's really not necessary. The reason is because when we have a prime p, all the inverses need to be unique. So that would be like from this list, if we have an a and b, if we say a not equal to b, there's going to be some a, I know this isn't very formal, but there's going to be some a times some b, which is going to be congruent to 1 mod 23 or any prime. What this really is this is Wilson's theorem. If we list out all these, if we list out the whole thing, the whole list, we end up, like if we did the whole thing from here, we have 22 factorial. But Wilson's theorem tells us that 22 factorial mod 23 is just 22 because each of these values has a unique inverse that's just going to multiply to 1 like this. But if we're saying that these 2 values are unique, they're not equal, then we never get this case. If a is not equal to b, we never get this square congruent to 1, except for just one case, and it's this 22. The reason the 22 is different is because 22 mod 23 is just minus 1. So if we look at that, we look at a as 22 and plug it in, but we write it as minus 1. Well, now we square that, minus 1 squared, that is going to be 1 mod 23. So our check for a primitive root is going to fail in this case, and we don't have to really check it because it's always, like, it's minus 1, so it's always going to be the one less than prime. We don't have to like go through them and wonder, is it this one or this one, because only this one can be minus 1, so this one is thrown out as a primitive root. You may be wondering about 1 again, because 1's going to fail this check, but we already eliminated 1, so that's why I don't care about checking 1, because 1's got that same property. You square it, you get back a 1. So what we're left with is a list of all of our primitive roots, mod 23. We have 5, 7, 10, 11, 14, 15, 17, 19, 20, 21. Again, knowing that they're going to pass this check because they have a unique inverse, they're not going to fail on this. And so the really quick answer, or like the short way to do it, if we didn't have to go through all the details, is to find all the quadratic residues with the Legendre symbol, eliminate, and then just cross off the last one, cross off the p-1 value, and everything that's left is going to be a primitive root. I mean, that'll still take you 2 or 3 minutes, but it's a lot better than if you had to go through and calculate and exponent all of these out. The other way you can do it, of course, like you can find, if you find one primitive root, like if you find 5, and then you raise this to all the different powers, you will get all the other primitive roots. When you reduce it, mod 23, Although I still think in this case it's a lot more work. That would probably be the best way. You know, if we had some other prime, a lot of other primes, this would probably be the way to go. But when we have this safe prime, I would say don't do that and just use the Legendre symbol just because the Legendre symbol gives us a lot of shortcuts to speed things up. Okay, that's it for today. Thanks everyone for watching. Have a good day.